Now, let's look at the different statistical based correlation models. We know how to calculate the correlation between the two securities using the statistical procedure, which is what we typically call as the Pearson's correlation coefficient, and typically represented by rho in some cases and r in some cases. But that statistical based correlation model, can we apply them to finance? Is it a best fit, or does it have any kind of limitations? So that is one thing which we are trying to see as a part of this session. So we know correlation primarily is a measure of the association between two or more variables. How strongly are the two variables related? What is the kind of interrelationship that is present? What is the kind of association that is present between two or more variables? And there are three statistical ways of trying to measure this correlation. The most common one, which we always keep seeing, is the Pearson correlation measure, which is more and more applicable if the data is more quantitative in nature. Whereas we have the other two, the Spearman's rank correlation as well as the Kendall's tau, which are generally applicable if my data is more and more ranked or typically ordinal in nature. Though Kendall tau is something which I can apply, even both of them I can very well apply to a quantitative data as well, ratio scale kind of a data as well, but there are a few limitations. But they really are a better fit if I am using them for ordinal kind of a data. So let's see the different ways of computation of these correlations, and do they really fit to the world of finance? And if not, what are the limitations associated with them? Now, just before we get into it, just to understand the typical reality of the financial instruments in the today's world, they are extremely complex instruments that are there. Lots and lots of innovations coming up in the financial space, resulting in extremely complex financial instruments getting created. And the market wise, if I am seeing, one, the products are very complex. Market wise, there is a huge market. Buyers and sellers are very huge in number, but there are lots and lots of irrational investors also who may go majorly by intuition rather than anything else. So the market is dominated even by those kind of players. There are different kinds of markets: the equity market, the fixed income market, commodities market, foreign exchange market, real estate market, and there is lots of interdependency or correlation that is existing between each of these markets. Financial institutions wise, there are hundreds and thousands of financial institutions offering various financial services to the clients. And looking at the products also, there are numerous products. On the equity markets, probably stocks are there. Fixed income markets, bonds as well as indexes. Even in the equity market, there are indexes. There are exchange traded funds. And the products have become more and more complex as well today. So which means any kind of financial model that I am trying to create, which will help me to take buy or sell decision, is going to be a very complex one. It can't replicate the reality of all these financial systems and products. But at the same time, there are so many financial models that are being used in the industry for various stuff. Probably if I just want to see the value at risk model, typically called as a VAR model, today it is implemented in lots of banks, and today it has become a part and parcel of Basel's implementations in terms of market risk. So basically we are seeing a value at risk kind of a model being a very good estimate of the market risk. We know that Black-Scholes model typically used for pricing the option, probably the one of the most accepted kind of a model, though it has a series of limitations, but it has been used very widely in the world of option valuation. And we have Coppola based models which are very good estimates of the credit value at risk, looking at the default of the credit portfolios. We can depend on Coppola based models. So it's not that the models are not there, but one single model may or may not address the entire gamut of markets and entire gamut of products that are getting traded on each of these markets. Now, if at all I have to build a financial model, what is that I really need to see? First thing, let's keep in mind that there is a clear difference between a financial model and a scientific model. When I talk about scientific model like E equal to mc squared, or when I talk about a scientific model, force equal to mass times the acceleration, in all cases, in all conditions, these relationships are going to work. Very few limitations that are existing. This relationship is constant over time. It's not bound with time. Even though this relationship might have been invented long back, even today that relationship will hold true. So what does that mean to us? It's a clear indication that when we are talking about a scientific model, even in the distant future we are trying to look at, any kind of environment we are trying to look at, the relationship may not change. But majorly when we talk about financial models, they are to a large extent empirical kind of models, because they are derived from the data which are more and more randomly behaving, trying to understand the best possible patterns in the data and relationships being derived. So depends on the market prices, how the market is behaving with respect to the inputs. Purely a human derived kind of a model may be applicable in some markets, may not be applicable in some markets, may change with time. A random behavior, unexpected behavior can quite comfortably crop up in those kind of products and markets. So we have to understand that the financial models are something that may change with time, need not be constant. Once decided on an equation, it's not that it will be the same forever. As the markets keep emerging, as the products keep emerging, the relationships may need to be revisited again and again. Right? So that's a clear differentiation which has to be in our mind when we are trying to talk about a financial model. Remember, it's not a scientific model. It will not be constant in all phases of time. So what we really need to understand and appreciate is any financial model is just an approximation of the reality. It's not scientific. So whatever the trusting you are doing to that financial model, it has to be critically only. You need to know what are the assumptions that have gone into that model, what are the limitations that are associated with model. All these are very much essential for us to understand. So every model, what are the problems? See, basically just to give an example, if I talk about a VAR model, it very clearly assumes that the returns are normally distributed. But what if the returns are not? We actually make an assumption that the returns of the assets are normally distributed. But the reality is the asset returns have fat tails. They are not normally distributed. There is a lot of skewness and kurtosis that is present in majority of the asset returns. So compared to a normal distribution, probably a model which is having a higher kurtosis is more and more appropriate. Similarly, when we look at a Black-Scholes-Merton model, whatever the formula it has given for the valuation of the option, there is one assumption that has gone into it, that it assumes that the volatility is constant for all the strike rates. But in the reality, we all know that the volatility for each of the strike rate could be different. And the reality is also is, especially with the currencies markets, the volatilities exhibit some kind of a smile kind of a thing, a shape like this. So it's not a flat like this, but volatilities are expected for different strike prices. So for very extremely in and out of the money kind of options, we see a higher volatility, whereas somewhere in the middle we are seeing lower volatilities. So a smile kind of thing is exhibited in case of currency markets, and a skew kind of thing is exhibited in case of equity markets. But the Black-Scholes model is assuming that the volatility is constant across. So what we are trying to suggest here is, every financial model, it has to be taken, it has to be considered with a pinch of salt. But a clear awareness of the mathematical inconsistencies that are present in each of these models has to be comfortably be understood. So that is one major dimension that we have to focus on. Then the real calculation issues of the model itself. What has really gone into the computation of the model? How do the values of this particular model are computed? What is the way the parameters are computed? Right? Based on the prices that are found in the market, what is the way the parameters are arrived at? Is it an ordinary least squares kind of a mechanism that is being used, or maximum likelihood estimation kind of a mechanism is being used? And I have to apply this, whatever the model that I have derived, whatever the way I have derived the parameters, I am applying it to value the products after a thorough testing for which the no new prices. So I am actually using the historical prices, based on that deriving the parameters of the model, using these parameters to do the prediction for those particular prices or for those particular variables for which the prices are not available. So a very important thing. So how better this A and B are computed is something which goes as the key in terms of the betterness of the model. The timing is very important. Sometimes I can't take the data when the economy is very stable, derive the parameters during the time period when the economy is stable, and use that data and use those parameters for predicting a particular economic variable during a recession. Right? It's as good as I can't use the non-crisis based data to model the crisis parameters. And that is where we have seen majority of the problems or majority of the deviations that come from the mathematical models are from the perspective of the timing not being understood appropriately and critically, and then being applied to the real world. So if the inputs are more and more unrealistic, the output you can't expect it to be realistic. So there should be heavy amount of stress testing. Good number of scenarios need to be identified. Extreme scenarios need to be identified from a stress testing perspective. All the knowledge relating to the recession, systemic market crashes, all these whatever have happened, they really need to be simulated and understood to the depth. And the good estimate of the risks of their portfolios in the distress times should be derived by using all these various simulation models. So the calculation of the parameters involved in the model becomes a very tough job as a part of the financial modeling exercise. Then there should be a clear clarity about the various limitations and assumptions that are built into the model. That is probably one of the things where people fail to understand The new Coppola correlation model, which has been very heavily used to model the default probabilities of the various credits in a portfolio, which has been used in the world of finance. There is a blind trusting on that particular model, and which could not anticipate the losses properly. Whatever the assumptions that have been used as a part of the correlation, they got violated in the real world. And initially it was assumed that there is a negative correlation between the equity tranche and the senior tranche of the ABS CDOs, but especially during the recession period, instead of a negative correlation between the two, it turned out to be a very heavy positive correlation, which means initially these two were expected to provide a kind of diversification, but during the crisis, both of them fell sharply, resulting in a very huge loss to the financial institutions. Now, the correlation assumption that has gone in terms of these two products, whatever the data that has been collected to compute the correlation was during the markets when the markets were doing well, but overall turned out into a disaster, especially when the markets were not performing well. So the Coppola model, the calibrations have been done with the good data and the time periods when the risks were not much higher. So there should be some amount of human judgment involved in terms of assessing all these various aspects of a financial model. So just to understand the different correlation coefficients, first thing which we always use in various aspects, the Pearson correlation coefficient denoted by rho, which talks about the strength of the linear association between the two variables. And more commonly we denote it by covariance between the two variables divided by the product of their individual standard deviations. And put it in another way, it is covariance wise, if I really want, it is each variable, I subtract the mean of it, and again the corresponding y variable, subtract the mean of it, add it over all the t's, and I divide it by n minus 1, because this is a sample related step. So this is how I get the covariance. Similarly, if I have to get the variance also, I take each of the values, subtract the mean from it, square it, add it over all the possible values, divide it by n minus 1. So once I do it, this is what I'm going to end up with in terms of computing the correlation. So I take expectation of xy minus expected value of x times expected value of y, divided by the square root of expected value of x squared minus expected value of x whole squared into square root of expected value of y squared minus expected value of y whole squared. And this is a very standard statistical tool we use in huge number of applications in finance. But what we also need to understand is, though we are using it in various aspects, it has its own set of limitations as well. A few things to consider here. It talks about the linear association between the two variables. But very often we will not see two variables having a linear relationship between them. We see non-linear relationships very heavily between the variables. They're behaving in a quite weird kind of fashions as well, which need not be linear in nature at any point. Then, see, in some cases, if the correlation comes to 0, it doesn't mean that these two variables are independent. The only meaning which the correlation of 0 is going to give me is no linear relationship between the two. It is not saying that these two variables are independent. This is a very danger area for us. when the correlation comes out to be 0 also, we can't typically conclude that these two variables are independent. We can only say they are not linearly dependent. They could be non-linearly dependent as well. So that is one major limitation with the usage of the correlation model. And it's also said, it talks about the real relationship dependency between the values only if their joint distribution is elliptical in nature. But lots and lots of scenarios where their joint distribution need not be elliptical, which means correlation cannot be used as a dependence measure at all. Then it also assumes that the variances of the two sets x and y which I am taking, they need to be finite. But in some cases, there is a very decent possibility that the variances, especially for values which keep growing and growing and growing, their variances need not be finite at all. And another major limitation with the Pearson correlation coefficient is it is not invariant to transformations. Means if I take the correlation between x and y, if I get some value a, I transform these two variables log x and log y, I will not get an a, I may get some b, which means the same variable after a transformation, it's going as something else. The correlations are changing. That is what I typically say. It is not invariant to transformation. But in some cases, if I have to really see that it's a very standard tool, then I need the even after the transformation, I need the correlation to be the same because it's a relationship between the two variables. And so one thing which people talk about is it is a simple approximation for the typical nonlinear relationship that can exist between the financial variables, but it is not a perfect match talking about the relationship between the two variables. But on the other side, we also have a couple of other measures which we said they are more and more applicable for ordinal kind of a data or the data which is having more and more ranked kind of stuff. So it's an ordinal measure. Again, the values wise it lies between -1 and +1 only. But here the real values of the variables are not important for me. It's only their rank. It's only their order is very much important, not the. So if I say the values are 1, 2, 3, 4, 5, or if I say the values are 1, 2, 3, 20 and 100, both will have the same kind of a treatment. Because rank wise, even in ascending order, if I see this is 1, 2, 3, 4, 5, even this is also 1, 2, 3, 4, 5. The correlation between these two numbers, if I want to do a correlation between these two, here I'll get it as perfectly +1. Because rank wise there is no difference between both the groups. But if I do a Pearson correlation between these two, it will not be +1 because it is purely talking about the change from the mean. Because mean changes, the correlation also will not be 1 in case of a Pearson's rank correlation, but Pearson's correlation. But in case of Spearman's rank correlation, it is definitely going to be 1. So it's a perfect correlation if an increase in the element xi is always accompanied by an increase in yi regardless of the numerical increase. So from here to here there is an increase. So here to here also there is an increase, which means rank is remaining the same. Simple way to put, as long as the rank is the same between two variables, you will get that the correlation is perfect. It's a pure non-parametric test because I don't need to know the joint distribution of the variables at all. Whereas the Pearson's correlation, it says that the dependency is more and more appropriate only if the joint distributions are elliptical. But here, even if I don't know the joint distribution between the two variables, I can very well use this correlation coefficient. So simple way is, if at all I am given two variables x and y, take them, then find the rank of x for each variable. For this particular value, what is the rank in this whole set? So for each of them, rank them. Similarly, for y, do the ranking of each of them, right? Then take the difference of the ranks, rank x minus rank y. Take the difference of them. Then square those differences. And once you have squared those differences, you typically go with the application like this. So probably if I am having the numbers, simply to look at 20, 30, 40, 50 are one set of numbers. 60, 30, 40, 70 are the other set. Now rank wise, this is 1, 2, 3, 4. In ascending or descending I can put. This is 1, 2, 3, 4. Now I'll take the difference between the ranks and square. 1 minus 3, 2 squared 4. 2 minus 1, 1 squared 1. 3 minus 2, 1 squared 1. 4 minus 4, 0. So overall the summation is going to be 6. So all I say is, now the rank correlation is nothing but 1 minus 6 times sigma d squared. Sigma d squared for me is 6 here, divided by n into n squared minus 1. N is 4 elements. N squared minus 1 is 50. 4 squared minus 1. So it is all coming out to 1 minus 36 by 60. So this is 6 by 10, 0.6, 1 minus 0.6 coming out to 0.4. So in this case, it is working out that the rank correlation between these two is somewhere around 0.4. So this is the way we can work out with the Spearman's rank correlation coefficient. Similarly, there is one more which is called as the Kendall's tau. This is also a commonly used kind of regression correlation measure in finance. More and more applicable again if my data is ordinal or ranked. Now, how I compute it? Let me take the same example, 20, 30, 40, 50. Then we have taken 60, 40, 30, 70. Right? Now, earlier when we did it, we first found out the ranks. 1, 2, 3, 4. Here it is 1, 2. Or probably I think there I have done, this is 30, this is 40. So it is becoming 1, 2, 3, 4. So this is what we have done when we are doing the Spearman's rank correlation. Whereas in this case, we actually take this entire set of values as pairs. What is that we say? Okay, first let's do it. Let's see. So the adjacent. So 20 I'll pair it with 30. 20 I'll pair with 40. 20 I'll pair with 50. Then 30 I'll pair with 40. 30 I'll pair with 50. 40 I'll pair with 50. So there are 6 pairs that I'm going to get. Okay. So what I typically see is, in this pair, in each of the pairs, I'll see if x is increasing, is y also increasing or decreasing. So if x and y, right, if x and y are moving in the same direction, either increasing or decreasing, we call that as concordant data, concordant pair. But if x is increasing and y is decreasing, or x is decreasing and y is increasing, we call it as discordant pair. And if x is same, y is either increasing or decreasing, or x is increasing or decreasing and y did not change, we call that as a tie and we don't even consider that. Now, let's see, okay, first pair. The first pair is 20, 30, and here it is 60, 30. The second pair 20, 40, and here it is 60, 40. The third 20, 50, here it is 60, 70. The fourth 30, 40, here also it is 30, 40. Then it is 30, 50, 30, 70. And finally it is 40, 50, 40, 70. There are 6 such pairs. Now I'll see, okay, X there is an increase, but Y there is a decrease. So this is what I call as a discordant pair. X there is an increase, Y there is a decrease. So this is also a discordant pair. X is an increase, Y is also an increase. So this is a concordant pair. X increase, Y increase, still a concordant pair. X increase, Y increase, a concordant pair. X increase, Y increase, a concordant pair. So in this, we have NC, the total number of concordant pairs, as 4. ND, the total number of discordant pairs, is 2. So from here, we are trying to compute the Kendall's tau, which comes out as number of concordant pairs minus the number of discordant pairs divided by the total number of pairs. We have 6 pairs altogether. Multiplied by 6 minus 1 by 2. Sorry, here n is the total number of pairs, so 6 into 5 by 2. So overall 2 divided by 50. So this forms your correlation that is existing between the two variables on a Kendall's tau computation basis. So it's purely non-parametric, and in case there is a tie, any one of them, so if x and this is the same, then even if this has increased or decreased, we call it as a tie and we will not include it as a part of the computation of Kendall's tau. So this is the way these calculations are typically done. And finally, now that we know that these are the 3 correlation measures, if we are looking at the various non-parametric correlations, which means either the usage of Kendall's tau or the usage of the Spearman's rank correlation coefficient, they are used quite comfortably by the rating agencies as a part of the rating categories, because rating categories are always like more and more ordinal in nature. So they are very much applicable for analyzing the rating categories. They are used in understanding the dependency of the market prices with respect to the counterparty risk. Wherever the observations are more and more ordinal kind in nature, they are better to use. But they are less sensitive to outliers. Probably sometimes it's a good thing, sometimes it is a limitation as well. As I said earlier, numbers like this as well as numbers like this, both are giving us the same kind of correlation for us when we are going with this particular mechanism, which means even if this kind of heavy values are coming out, it does not identify such kind of heavy deviations that are present in the data. Even if there is a severe loss that has occurred in the past, that does not get numerically assessed, because rank wise it looks as if it is still the 5th one. So the difference becomes completely narrowed and extreme things get completely out of the analysis. And even when we are taking a data which is having a very high risk value in the past, today it shows that there is not much of a risk that is actually present. So that becomes another major problem with using the non-parametric correlation problem. And at the same time, especially when I am going with Kendall's tau, many non-coordinate, non-concordant and non-discordant pairs, if they are there, they discard the entire tau calculation itself. Especially if I am having too many ties, we whatever the calculation we are doing, it becomes more and more distorted. And application of the statistical correlation concept becomes very limited in finance. It is slowly moving towards a world where quantitative experts, they are coming forward for developing specific financial correlation methods, which we'll be seeing. The copula based mechanisms are becoming more and more appropriate in terms of deciding the relationship between the various parameters and the variables. So that's all. But we need to understand the various statistical measures, the kind of limitations they carry, the kind of mechanisms in which the computations do happen, so that we can take the decisions quite appropriately in any of the investment scenarios, right?